As I said, an event is nothing but a subset of the sample space. The sample space is a set, so an event is a set. And we can do all sorts of set operations on events and count the and compute the probability on such sets. So if we have sample space S and events, let's call them actually events, let's say E1 and E2 are two events. And suppose I want to ask what's the probability of E1 union E2. Okay, so suppose the experiment is tossing a coin 5 times, and E1 is the event that correspond to the outcomes where the first toss shows a heads, and E2 is the event that corresponds to the outcomes where the last toss shows tails. E1 union E2, we are saying what's the probability that you toss a coin 5 times and the very first toss is heads, or the last toss is tails, okay? And we know what's the formula for E1 and E2, in union E2 in terms of computing the size or cardinality of such a set. This becomes the probability of E1 plus the probability of E2 minus the probability of the intersection of these two, right? So if we have, this is the event E1 and this is E2. Remember when we talked about the cardinality of the union, we said that elements in the intersection are double counted, and this is why we subtract from this. Now, if the two events are disjoint, then we have P of E1 union E2 is P of E1 plus P of E2. Okay? Now, this is again just follows from what I wrote before, because then the probability of the intersection of the two is 0, and this follows from that. Okay? But we can do, again, we can do any other set operation. So for example, I can say, what is the probability of the complement of E1? Okay? So again, remember that, so if I take the example E1, again, the experiment was I tossed a coin 5 times, and E1 was the first toss shows heads. What does it mean to compute the probability of the complement of E1? I'm saying, what is the probability that the first toss was not a head? Okay, and this is what the E1 complement is. This is really the probability of S minus E1. This is the formula for the complement, right? Because the universal set in our case is S, the sample space, and this will be the formula. And the very important rule here that we can use is that this equals 1 minus P of E1. Okay, this is a very important rule, because if I say what's the probability that the first toss is not heads, and you have already computed that probability, then the probability of the complement is just 1 minus that. So it's very important to keep this in mind here. Okay, now you can do the same the probability for the set difference of two events. You can do it for any set operations that you want to define. Okay, now one very important concept when we talk about probability is the notion of conditional probability. And we usually write it like P of E, this bar F, okay? What is bar F? The way we read it here is that the probability of E given F, okay? And what is the definition of this? The probability of E given F? It is the probability of E given F is the probability, that what we say the joint probability of E and F, divided by the probability of F. Of course, for this to be well defined, the probability of F cannot be 0. Okay? So intuitively, what is the probability of E given F here? What this is asking about, that if I told you that event F has already taken place, that event F occurred, what is the probability of E? Okay, so sometimes it might be that the fact that F happened has absolutely no implications on the probability of E, in which case we are going to call these two events independent. Or sometimes just telling you that if happened, all of a sudden that can affect the probability of E. Okay, so if E and F are independent, they have really nothing to do with each other, what ends up happening is that what we get is P of, so let me actually first write this without having a fraction. So if you look at this, what this says that probability of E given F times the probability of F is the probability of E intersection with F. Okay, now if you do the calculation here and you find that P of E times the probability of F is the probability of E and F, this is basically we are saying E and F are independent. Okay, but it's very important for you to see here what happened. This really here in red is the formula for this conditional probability. Okay, now what happened? What's the similarity between these two, or what the difference between these two? Really the difference is this P of E given F became P of E. Okay, so what does that mean? I am saying that P of E given F in this case equals P of E. This intuitively is saying that if you told me that if happened and asked me to compute the probability of E, this is exactly the same like computing the probability of E without knowing that if happened. Okay, so the left hand side here, probability of E given F, is saying what's the probability of E given that you told me if happened. What's on the right hand side? I'm asking what is the probability of E regardless of anything, any knowledge about if. If these two are the same, then what are we saying? That the probability of E, given that if happened, is exactly the same probability as E without knowing anything about whether if happened or not. Okay? And this is why intuitively, or this is really the meaning of two events being independent, that they have absolutely nothing to do with each other. And the probability of E given if happened now becomes just the probability of E. Okay, and this is a very important concept. There are two concepts here. There is a conditional probability concept, and there is the concept of independence. Okay, so we can look at an example here. Let's take as an example and say, suppose that our experiment is generating binary vectors of length 4. Okay, so binary vectors of length 4. Okay, again under the assumption that 0 and 1 have equal probability, so we have really in S2 to the 4 or 16 possible vectors. The probability of each one of them is 1 over 16 and so on. And suppose we take the two events E, the string begins with S, or the binary vector, the vector begins with 1, sorry, not with S, with 1. And let's take if the vector contains an even number of ones. Even number of ones. Okay, the question is, are E and F independent? Okay, in other words, if I told you that the vector begins with 1, does that affect the probability that the vector has an even number of ones? Or I could ask, if I told you that the vector has an even number of ones, does that affect the probability that the vector starts with 1? To answer this question mathematically, we have to compute P of E, we have to compute P of F, we have to compute P of E intersection F, and we have to ask the question, is P of E intersection F equal to P of E times P of F, right? So we have to ask this question. If the answer is yes, then they are independent. If the answer is no, they are not independent. So we have now to do these calculations. What is the probability of E? The probability of E, we're asking what's the probability that the vector begins with 1, okay? So if the vector begins with 1, there are 2 to the third possible vectors that begin with 1, right? Because you fix 1 in the first position, and then for the other 3 positions, you can have zeros or ones, 2 to the third. And we divide by the total number of vectors, which is 2 to the fourth. We end up with 1/2. But also an intuitive way to answer this question here, just think about it, that since 0 and 1 appear with probability 0.5, half of the vectors are going to start with 1, half of the vectors are going to start with 0, right? So the probability of E is just 1/2. Sorry. Okay. The probability of E is 1/2. The question is that what's the probability of F? The probability that the vector contains an even number of ones. What does it mean, or what are the vectors that contain number of ones? The vector can have zero ones, because that's an even number, right? So 4 choose 0. And if we take this, the probability of such a vector that has 0 ones, it is 0.5 to the fourth, right? So the 4 choose 0 is the number of vectors that have 0 ones in them. I'm choosing 0 positions for these ones, times 0.5 to the fourth. Or the vector can have exactly 2 ones. There are 4 choose 2 such vectors. Each of them appears with probability 0.5 to the 4. Or the vector can have 4 ones in it, because that's another even number. 4 choose 4, and it is 0.5 to the 4. 4 choose 0 is 1. This is 0.5 to the 4. 4 choose 2 is 6. 6 times 0.5 to the 4. 4 choose 4 is 1 times 0.5 to the 4. So we have 1 plus 6 plus 1. This is 8 times 0.5 to the 4, right? And this, remember that 8 is 2 to the third, and 8 is 2 to the third, and 0.5 to the fourth is really 1 over 2 to the fourth. This becomes 1 over 2. It's 1/2. Okay, so the probability of F is also 1/2. Let's look at the probability of E intersection with F. So what are we talking about here? We are talking about what's the probability that the vector starts with 1 and has an even number of ones. Well, what are the vectors of size 4 that start with 1 and have an even number of ones? They are, if you start with 1 and even number of ones, you can have 2 ones, in which case you can have 1, 1, 0, 0, or 1, 0, 1, 0, or 1, 0, 0, 1. These are the vectors that have 2 ones in them, and the very first element is 1. Or you can have 4 ones, in which case you have to have this. So there are really 4 of them, and each one of them appears with probability 1 over 16. So 1 times 4, 4 times 1 over 16 is 1/4. Okay? So now we know P of E is 1/2. P of F is 1/2, and P of E and F is 1/4, and P of E times P of F is 1/4. Since these two are equal, it follows that E and F are independent. Okay? These are independent. So this is how we check independence of 2 events. You compute the probability of each of the events individually, then you compute the probability of the intersection. If the probability of the intersection, or what we call the joint probability of the 2 events, equals the product of the probabilities of the events, then the 2 events are independent. And again, keep in mind that formula for the conditional probability P of E given F is the probability of E and F divided by the probability of f. And one point I want to make here, and one maybe last point about this notion is, if you look at P of E and f, we said it is the probability of E given f times the probability of f, right? But if you think about it, the intersection is symmetric, right? E intersection with f is the same thing as the intersection of f and E. Therefore, I could also write this probability of f given E times the probability of E, okay? So you can either condition E on f times the probability of f, or you can condition f on E times the probability of E. These two are equal, okay, no matter how you do it. So again, the question is that when I was talking about the joint probability of vectors that start with 1 and have even number of ones, it's the same if I want to first say, conditioned on even number of ones, what's the probability of starting with 1? Or conditioning on starting with 1, what's the probability of even number of ones? Again, under this equality here, both sides on the left-hand side, P of E given f times P of f, and P of f given E times P of E, they are the same, okay? So you can do it either way in terms of calculation. The very last word I want to say that I have been talking about two events here, but really you can think about if you have more than two events. Suppose you have n events here. We can talk about them as being pairwise independent. Okay, pairwise independent, as the name indicates, that if you take any two of them, they must be independent. Okay, so this means P of EI intersection with EJ equals P of EI, P of EJ for every I and j that are not equal. Okay, I and j between 1 and n. So this is pairwise independent, but we can also talk about mutually independent. Mutually independent. And here, when we talk about E1 and E2 and all the way to En being mutually independent, we are saying that for every subset of those n events, with the subset, of course, the size of subset being greater than 2, we have the probability of the intersection of the events in this subset equals the product of the probability of those events. Okay, so this is mutually independent here. It's a stronger assumption or a stronger condition we put on those events. Mutually independent, of course, implies that they are pairwise independent, because think about subsets of size 2, which is contained here. So, and it satisfies that also for subsets of 2 events, they are independent. So if they are mutually independent, they are for sure pairwise independent. However, if they are pairwise and independent, it doesn't mean they are mutually independent, okay? And for example, I will not solve it for you, but if you toss a coin, a fair coin here twice, and think about the following events. E1, the first toss is heads. If you think about E2, the second toss is heads. And if you think about E3, that both tosses are the same, both tosses yield the same outcome. So either both are heads or both are tails. If you look at these here, if you think about these, they are pairwise independent, but they are not mutually independent in this case. You can do the math. You will find that if you take the probability, the joint probability of any two of them, it's going to equal the product of the two probabilities. But when you look at the three-way probability, the probability of the intersection of E1 and E2 and E3 in this case, it's not going to be equal to the product of the three probabilities. So this is an example of three events that are pairwise independent, but they are not mutually independent.